Hello, my name is Carlos Infante Ferreira. In this lecture, I will introduce you to heat pumps and their role in the energy transition. In this lecture, we will talk about the working principle of heat pumps. Then we will discuss the advantages and limitations of heat pumps. And finally, we will look at the role of heat pumps in energy transition and integrated energy systems. To understand the working of heat pumps, let us take an example of a refrigerator, which is what we all have in our houses. A refrigerator works on vapor compression cycle, which is very similar to what is used in heat pumps. The working of a refrigerator can be explained using this figure. The insulated refrigerated cabinet, which is cooled, is shown here in blue, which is at temperature Tc. The room to which the heat is released is shown in orange, which is at temperature Th. The refrigerant goes around the loop along the two reservoirs through which heat is exchanged. The refrigerant takes up heat from the cold reservoir, shown here as Qc. It is then compressed by the compressor using electrical work, Vcomp, which further increases its temperature and pressure. The heated refrigerant then releases heat to the hot reservoir through the condenser, shown here as QH, and is then returned back to its original pressure using the throttle valve. In this way, heat is transferred from cold to hot reservoir. Using the first law of thermodynamics, we get the relation between QC, Vcomp, and QH. Now, to determine the performance of the cycle, we define the coefficient performance, or COP, as the ratio of useful heat delivered to the electrical input. Mathematically, the same is represented as shown here. In practice, we have a more complex system used to drive the working fluid in cold and hot sites. For such a system, additional electrical work is required on cold and hot side, shown here as Vpump C and Vpump H. Consequently, COP of the cycle becomes this as shown here. This is because the net electrical input for the cycle will also include the extra pump work on cold and hot side. Furthermore, if all the processes are considered reversible, then it can be derived that the COP of the heat pump will be this ratio of temperature of hot reservoir to the temperature difference between hot and cold reservoir. The actual COP of the heat pump is more complex and differs from the reversible heat pump COP. This graph shows the variation of COP along the y-axis and sink temperature along the x-axis for a fixed source temperature. The green curve shows the COP of the actual heat pump, while the blue curve is the reversible COP of the heat pump. For this case, the environmental air at 0 degrees Celsius is taken as the heat source. For the heat sink temperature of 40 degrees Celsius, we get a COP of about 3.1. If we use groundwater at 10 degrees Celsius as heat source, the COP becomes 4.2. Similarly, for aquifers or ATES, at 20 degrees Celsius and geothermal heat at 30 degrees Celsius as heat source, the COP of the heat pump for 40 degrees Celsius sink temperature will be 6.3 and 12.5 respectively. So we see that the COP of the heat pump depends largely on the heat source and sink temperatures. If you can use aquifers and geothermal heat sources, then we can have high COPs for heat pumps. Let us look at heat pumps available in the market. In this image, seasonal COP for various refrigerants is plotted on the y-axis against specific costs of the heat pumps on the x-axis. The machines plotted in the image are air-water heat pumps with 150 kilowatt heating capacity and 40 degrees Celsius sink temperature. The blue region represents the commercially available machines. These machines are designed for temperature differences of about 8 Kelvin. For these machines, the seasonal COP is about 2.4. If the cycle is improved by investing more in heat exchangers and having larger area, then smaller temperature differences can be achieved at the heat exchanger, resulting in higher COP of the heat pumps of about 2.8. Although this would increase the investment cost of the machine, the specific cost remains the same. This is shown in red in the image. Further, by using higher efficiency compressors, the COP of the heat pumps can be improved further to about 3.1. This again increases the investment cost while the specific cost remains unchanged. This is shown in orange in the image. Now let us look at the role of heat pumps in energy transition with an example of energy requirements of a household in the Netherlands. Here, the energy balance of Dutch household is shown for the entire year. The weekly energy consumption is plotted on the y-axis with a week number on the x-axis. The weekly energy consumption of gas for heating and cooling purposes is shown in blue. The electricity usage is shown in red, and the electricity production using PV panels on the roof is shown in green. Let us consider the impact of substituting the gas system by heat pumps. If we use an air source heat pump, which is mostly used, then since it has low COP, this means a lot of electricity is required to meet the demand. The net electricity import will be greater than 4,000 kilowatt hours per year. Using a groundwater source heat pump, the electricity requirement will be lower than for the air source heat pump, but still will be 2,700 kilowatt hours per year. However, using the same for individual houses is not economically feasible. If ETIs, ECAST aquifers, are considered, which can only be used together with neighboring houses, then things become better. The net electricity import becomes about 1,500 kilowatt hours per year. Further, if we use low temperature geothermal source heat pumps, then since they have high COP, the net electricity import reduces to 57 kilowatt hour per year. So we have seen that by using heat pumps for energy integration creates electricity demand peak in winters. However, storing the excess thermal energy available in summer can be used to cover the heating demand in winters. Let us now recap what we have covered in this lecture. We looked at the working principle of heat pumps, where we discussed the vapor compression cycle and the coefficient of performance, ECAST, the COP. Then we looked at the advantages and limitations of heat pumps, where we looked at the impact of source and sink temperature on the COP of the heat pumps. And finally, we looked at how the heat pumps can be used for energy transition, where we looked at how heat pump creates electricity demand in winters, and that excess heat energy available in summer can be stored and used to reduce the extra demand created due to the heat pumps. Thank you for your attention.